we have defined, right? Um, we have defined that sigma algebra generated by random variable. I mean, rather a family of random variables, right, or a sequence of random variables, and yeah, and we have done some proof of those things, that intersection of sigma algebra is also sigma algebra. The countable intersection of sigma algebra is also sigma algebra. And then we define what is a Borel function. Okay. Then yeah, then we are then we were about to discuss this. We are discussing that about f is a Borel function and x is a random variable. Composition f of x is sigma x measurable. So we have already defined what is an sigma algebra generated by a random variable, right? I mean, yeah. So it's a sigma algebra generated by random variable. So x is a random variable. Okay. And sigma x is nothing but x inverse a, such that a belongs to Borel of R, right? So yeah, and this is an element of F, correct? And what is F measurable? We have yeah. So this is the definition of F measurable. X is said to be an F measurable if X is said to be F measurable if I mean this X belongs to A, is a element of F for every Borel set. This for every Borel set, this thing, correct? So yeah, so we have so we have done it for random variable, correct? Now the thing is, it is little bit more of what does it say? This recent statement. It says that it is mostly the composition, right? I mean, x is a random variable and f is a Borel function, right? So Borel function is what? What is I mean, it's a R to R. So x is a random variable. This perfectly works fine, right? I mean, so today is what? I mean, you see whether this composition f of x is well defined or not. I mean, it works fine because x is a map from omega to r, right? And f is a map from r to r, right? That's correct. So f is a map from both r to r. So in a sense that f composed of x, so it is nothing but f of x. I mean, this is pretty much well defined, right? I mean, yeah. So x takes you from omega to r, and f is taken from you r to r. So in the sense that f of x is a map from, it's a composition, right? It's a composition from capital omega to r. So, so now what we have to show that this fellow is F compose X is sigma X measured. So how will we go about it? Now how will you do? How will you show this? I mean, you see, so F is a function from R to R, right? Correct. And it's a Borel function. So F is R to R and Borel function. Correct. So so that means what? This means by definition that F inverse of B, right? Is it's an element of Borel's is an element of Borel's. So so in a sense, so what does it imply? I mean, it implies that yeah.
So our two students are waiting to join, sir. Can you let them in?
Only one Rishabh, right? Is there anyone?
Maybe Khush Kataria also.
Who?
Khush Kataria, sir.
I am already in, sir.
Uh, yeah, so this Rishabh things is always he goes out, comes in. I don't understand it.
Sir, some network issue and sometimes sir, when call comes in between, then call disconnects. Sir.
Thank you, sir.
Yeah. So, it's okay. Yeah. So in a sense that what does it mean that some f of x, because f is a function from, so this is nothing but x is an element of f inverse b. Uh, right. I mean, So f of x belongs to this means x belongs to f inverse b, right? And 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 uh, and these fellows. So what about the sigma x, whatever we have written? This one is so. You see, definition of sigma x is this one, right? So we can, yeah. So first of all, x inverse A is this one. So you see, right? This is my x inverse A, correct? This is the definition of x inverse A. That is what uh, we have done for all A in and 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 this is my sigma x. Uh, yeah, and sigma x is defined as is. So what is sigma x definition? So x inverse is such that so now here what we have uh, what we have yeah so this B is a Borel set. So B is right, and I have X is an element of F inverse B, right? Yeah. So, I mean here I have But this is nothing but, I mean, f of x belongs to B. So So basically, what I have to prove here, I have to prove that f of x is sigma x measurable. Right? So f of x is sigma x measurable means what? That so something is x, a random variable x or a function omega is said to be f measurable if I mean, this is the definition, or x inverse A belongs to F, right? This is this thing. I mean, if x inverse A belongs to F for any A in Borel sigma algebra, right? So then then the x is called F measurable, right? So x is called F measurable if x inverse A is an element of F, right? Now, what I have to prove here, I have to prove that if compose x is sigma x measurable. So what does it mean? This means that acha, this means what? That Correct. This is what we have to prove, right? I mean, just one moment. I mean, if compose X inverse, uh, we can think of it as some. Uh, let's call it D, something. Now, now, what about now? How will you write this thing? How will you think of this f of compose inverse of a set D? Okay. So this is I mean, this fellow is nothing. So, sorry. You say so because what I want to make sure here that look, x is omega to r, f of x is r to r. So in a sense that f compose x is a map from capital omega to r, right? Correct. Because x is from omega to r, f is taken again from r to r. So f compose x is nothing but a map from capital omega to r. Okay. So that is what I have written here. Because small omega is an element of this thing, right? Capital omega. And this is nothing but this. And So yeah, so in a sense that I have to show that this this is, I mean, by definition, this is an element of F, or correct. So my this D is nothing but so D is a, so this D is the element of Borel sigma algebra. D is the element of Borel sigma, correct. And what I have to prove, I have to prove that this is uh, this is an element of sigma x. Sigma x is what? Sigma x is nothing but uh, this type of set, right? Or yeah, so in a sense, this one you can also write it as omega belongs to capital Omega, such that x set, correct? Yeah. uh, yeah, you can write it like this. You can write more precisely like this. Correct? So in a sense that so f compose of x inverse is nothing but omega belongs to omega, f of x belongs to d, and this belongs so therefore omega belongs to this and f of x this is a this, and this is because what kind of these things we have? We have the because you see something is f measurable means that you will have the inverse image is you will have the inverse image is the in the that that collection of set, correct? and uh, and my sigma x is this type of this thing, so f of x inverse d, correct, this fellow, and f compose of x is from omega to r, right? So something you choose from here, so choose from say d here, that inverse should be here in the sigma algebra, correct? And that is what we have able to see. I mean, because okay, so you can say that okay, you are writing that this is f, so in a sense that this is f measurable, but you see f measurable, the definition of f measurable is I mean, this is f measurable, right? X inverse of a such that x omega belongs to a. I mean, this should be belongs to f, correct? And uh, and I am saying you that and, um, and I am saying you that this because f inverse b, this fellow is again a Borel set, right? I mean, because you take something from the Borel sigma algebra, the inverse image, because f is a map from R to R. So in a sense that here you have R, BR, and again you are here you have R, BR, right? So whatever you take from here, that inverse image is will be in the Borel set here, right? Will be in the Borel set here, and yeah, I mean the for example here f of x omega belongs to d, correct? So in a sense we can write one line here. So correct, x omega belongs to f inverse. and x omega is again from, so therefore this is sigma x measurable, because what we have to show that that this is some sort of Borel set, and because this F inverse D is an element of here, so this is a Borel set. This is a Borel set. Okay. I mean, is it clear to you or there is some doubt? Hello? Hello? Is it clear? Hello?
Yes, sir. So can there be any situation such that, hello,
Sorry, yeah,
hello?
repeat. Yeah, tell
So
me.
there, can there be a situation when the map we are, the mapping we design doesn't go to the Borel set only? Like, sir, measurable set it goes, but not Borel set.
Yeah, I think that is possible. That construction is possible. Okay. Uh, this says that if f is Borel function, it's a random variable, then f of x is a sigma x measurable. So therefore, what you are saying, so there are conditions. F is Borel, x is, then this will happen. So what you are saying, that is possible. We have to construct. We have to see that example. But yeah, I mean, so the here the argument is this one, that x, this is Borel set. So in a sense that this is I don't have place to write, so I can write it here. So in a sense, what we came here is omega mhm. So mhm. No, so there is a mistake, I mean, little thing which I have to get taken care of. I mean, we can write it like this, because just a moment. So, so x omega belongs to f inverse t, right? And this is the element of Borel's for yeah. So in a sense that, so you have omega, you have r, you have r. So f is a function from r to r, x is a random variable from omega to r, and f compose x. So X first takes it to this, and then F takes it to here, right? So in a sense that we can. Okay, so we can see it again like this. F inverse is this, right? And X inverse is this, and you state a small omega. First you go here and then here, right? So this is my F compose X. Here the point is X of omega, and you again act it with F, you get F of X. And then similarly you so what we are writing here is here, right? I mean F inverse D. So if you have a set D here, F inverse D will be here, correct? F inverse D will be here. So here will be my F inverse D. That is what we are talking about. And this should be element of Borel sigma, because this is an R, so you have R BR. The moment you say that, that means that F of X is sigma X measured. I mean, and naturally, I mean, they I mean, when we studied this thing, so what I mean, look, this X belongs to A. This and this both are same, right? Correct. These both are same. So either you write as X omega this, or X inverse A means those omega such that X omega belongs to. That is what we. And you can again write this as yeah, you can again pull it off here like omega such that X inverse F inverse and this is will be an element of F, because here I have omega and F. So what is this fellow? This is nothing but X inverse F inverse. We can write it F compose X whole inverse of. This is the second. Yeah. So this is F measurable. what we have to prove is sigma x measurable. So sigma x measurable means so sigma x is this set, right? Sigma x measurable means I have to show something is in sigma x. I have to show something is in sigma x. And what are the element of sigma x? Sigma x are those things such that x omega is an element of A where A is a Borel set. And that is what we are doing here, that F inverse D is a Borel set. Correct? I mean, not X, I mean, X omega belongs to F inverse D, which is a Borel set. That is what we are doing. So in a sense, that sigma X is X inverse A such that A is a Borel set. And what we are able to show here that this X omega belongs to F inverse T, and these are Borel set here. So therefore, this is a sigma X measurable. So I have to prove that this is sigma X. Yeah, you can think of it. I mean, this needs little bit thinking, and yeah, if you want, I can discuss it again. Okay, let's take some 10-15 minutes break and then we'll start again. ठीक है?
Yes, sir.
Yes,
Yeah.
sir.